Hi everybody, today we are going to talk about one of my favorite lessons, and that is using the properties of logarithms to evaluate and transform expressions. So this is one of the most important lessons we're going to talk about in Unit 1B along with the next lesson. So make sure you take really good notes, and you may actually want a separate sheet of paper as well, because some of the spaces in your Springboard book get a little tight. So I'd recommend maybe having a separate note sheet if that's your style. Okay, now we talked about in the last lesson how we can use our calculators, and we can use Alpha Math if you have a newer calculator, which I know many of you do, in order to type in this logarithm here. But what if you're like Miss Sechek and you live in the olden days of the late 2000s and you only have a TI-84 without Alpha Math and prettiness that is Math Print? Well, that's where the change of base formula comes into play. So log base 5 of 28 can be typed into our calculator using the change of base formula, which basically says that the anything can be rewritten using the common log or the natural log in our calculators, where the value of log 28 divided by log of your base is going to give you then your approximation here. So it's the same exact thing. So for instance, if you again don't have a fancy calculator to do this, log base 5 of 8 we could rewrite as log 8 divided by log 5, and we'd get the same answer. So just to show you that Alpha Math, log 5 of 8 is this, or again, log 8 divided by log 5 also gave us that exact same value. Okay, so notice it's the same thing. So just in case you ever get stuck on a desert island without a fancy new calculator and you just have a TI-83, this is how you could do this. Okay, this also is handy when it comes to graphing. If you can't, you can graph, similarly like this. And just to show as well, log 8, or excuse me, ln 8 divided by ln of 5, again, the base, same value there. So again, the change of base works with both the common and the natural log. I always like to remember the base goes on the bottom, and then you won't forget. Okay. So same idea here when we rewrite this. Like I said, if you want to type this in the calculator, log of x divided by log of b. Again, this could help you with graphing, or again, ln x divided by ln b. Same idea there. Okay, for the variable problems. Now, we've talked a lot about setting up these equations and solving, and I told you we would focus more on how to solve with logarithms. Now, notice here this problem talks about a doubling time of 1 hour, a colony that initially contains 20 bacteria, and we want to write a function n of t where t represents the number of hours. So if we're starting with an initial population of 20, and think back to our geometric sequences, our common ratio here is 2 then, if we're talking about doubling time to the t hour, right, for our time here. So we can use this function now to talk about when is this going to equal 10,000. And so far we've talked about using our calculators to look for an intersection, but let's say we don't want to spend the time playing around with the window. How can we solve this algebraically? Well, looking at order of operations, we are going to start by dividing by 20. Okay, and that's what we're going to get when they talk about rewrite this. So on the next page, so that 2t is isolated, we're going to write this so that we end up with 500 equals 2 to the t, since we divided the 20 away. And then we can rewrite this using our change of base that we talked about before, log with a base of 2, since the base of the exponential is going to match the base of our log of 500 equals our time, right? So now you have some options. Okay, you could use Alpha Math, or if you're going to use change of base formula, like the book talks about, we would have log of 500 divided by log of 2. And either way you slice it, you should get that it would take approximately 8.966 hours, aka about 9 hours for this population to reach about 10,000. Okay. Now, this is where the fun begins. And if I could put about 1,000,000 stars on this page, I definitely would. So we have star all over the place for these next couple of boxes. Okay. The properties of our exponents that you've been dealing with probably since your pre-algebra days are going to relate to our properties of logarithms. And one of the big things we see here is if we are multiplying like bases of exponents, we add their exponents here. Same idea here. If you're multiplying logs within, you can expand them so that they're addition. So multiplication and addition are buddies. The same way division and subtraction are buddies. We could break up division to be subtraction or combine subtraction down to be division. And then the power rules work kind of the same way. We've actually talked about this a little bit before when I've previewed solving before. You can move an exponent out front of a logarithm. And then anytime you have matching bases, these exponents have to be equal. Same idea. If you have like bases here with your log, the values inside here have to be equal. Okay. So kind of to see this in action, just to kind of, prove some things, they have here asking us to compare the two graphs of log of 3 of x versus log of 3x. And then we have log of 3 plus log of x. And what we're going to notice here is when we graph this, zoom 6, just to see a standard graph, what we're going to see is these graphs are the same function, right? These functions are the exact same graph, so thus proving again that these are equal. So when in doubt, you can always check it graphically, is an option. Now, so again, still using my stars everywhere. They are the same graph. Okay. Now, these log functions are also going to hold for our common log. So to rewrite these, again, the logs, if we rewrote them as natural logs, we're basically just changing all of these to have n ln instead. So ln of m times n is going to equal ln of m plus ln of n. That looks funny. And then we have ln of m divided by n is ln of m minus ln of n. Right there. Dividing on the bottom, kind of the second term there. Ln of m to the n power means we could write that n out front. And last but not least, whatever the ln is inside here. So ln of m equals ln of n, then m is equal n. Okay, so they work whether we're talking about common log, natural log, really logs of any base as long as they have the same base. Now comes the fun part, which again, you guys may or may not want to expand at times to a different sheet of paper, but we're going to look at some of these problems to expand these out. Okay, so they give us one example here, and then they want us to start expanding these as well. So notice here we have a couple of things going on. We have multiplication between 3 different values, and we have an exponent. So what we're going to do to start is we are going to take this log, and reminder, multiplication of logs within these logs is going to turn into addition. Okay, so log of y to the third. So we're expanding these out. Now we can also take this this exponent and move it out front as well. So this would expand it to its fullest potential because we have that exponent brought out front. Okay. Another example then would be like letter B. Notice we are going to break this up so that we're going to break up the numerator first. So ln of x and then ln of y. and then we're going, since they were being multiplied, we're going to make those addition. And then we're also going to subtract then that ln of z to the fourth, because we have that division. Well, again, that 4 can be moved out front, so we have ln of x plus ln of y minus 4 ln of c. Okay, and that one's completely expanded out. All right, now these last couple examples are a little crazy. So let's look at c. Okay, notice we have a couple things going on here. I'm going to actually start by rewriting this as ln of x divided by x squared plus 1 to the 1/2, okay? Because we can rewrite a square root to the 1/2 power. And then we can break this up. So we have our ln of x minus ln of x squared plus 1 to the 1/2. And then last but not least, we can move that 1/2 out front of our natural log, okay? Now, you're probably thinking, can't we do something with that x squared plus 1? It's addition, right? It's addition inside here, not multiplication. So we can't do anything further, right? This is as expanded as it's going to get because it's not multiplication or division inside the log to expand out, okay? Now, more important, quite honestly, than our expanding is condensing, and you'll see why when we start solving equations, why condensing is much more important, because it'll usually allow us to kind of cancel some things out. So they give us again an example here. It's a kind of a long one, so it's a good one to look through, and they kind of walk you through step by step. But let's start looking at some of these other examples here. So we have part A in the try these. Now, first thing you're always going to want to look for is there an exponent I can move back inside? So ln of x minus 1 to the third power minus ln of x. And then we have this subtraction, which we can rewrite as division. So we have the x minus 1 to the third power divided by x. Okay, and that's as simplified as that one is going to get, so we can leave it there. You don't have to like factor out the trinomial or anything on that, nothing crazy there. Now the next piece is, notice the brackets here are indicating that we're going to want to start here, and also notice that we have a 4 out front of both pieces. So what this is indicating to us is that we have to take that 4, and I'm going to keep the brackets here for a second, and we need to make sure that it is an exponent of both of these pieces, and we want to then condense here first. So we have log of x minus log of x minus 2 to the fourth plus, multiplied by, because that the addition turns into multiplication, x plus 2 to the fourth, okay? Now, another way of looking at this then is that because these were conjugates of each other, they actually could be combined further inside here, but we'll ignore that fact for a second here. Finally, to rewrite this as one singular log, right? We have log of x and then the minus, so log of x minus 2 to the fourth, x plus 2 to the fourth. And then we have that written as one log. And again, we could officially simplify a little bit more inside of here, but we're just gonna let it go for now, okay? Finally, down here for part C, we have this value up front. And again, we're gonna wanna take into consideration that that is going to be a piece inside of here. Now, we can also start by looking inside of here. Know that this is going to be a part of both. But let's look at this so that we are dividing first, right? We're getting rid of this subtraction. So we have x plus 2 divided by x squared minus 4. And the reason I want to look at this first is because a reminder that we have x plus 2. X squared minus 4 is a difference of two squares that if we factored it, oops, should get 2, these could cancel, right? And we could simplify there. Now, we don't have to. I wouldn't, you don't have to, but for this case, but it sometimes might be a nice trick. And then last but not least, we would want to take ln, and if we move that 1/2 inside, it really is the same thing as saying the square root. Okay. All right. Now, one really important thing to know, right? All of these were able to be condensed down into one singular thing because they were the same base. So notice here, we would not be able to do anything with this into a single logarithm because log base 2 is not the same thing as log base 5, right? These need to match so that we cannot write them as a singular expression. They have to have the same base, which is going to become important to us when we start solving the equations with this. Okay. All right, I swear we're almost done. We're getting there. All right, last couple of things. A reminder that you can help use the change of base formulas to help you plug things into your calculator and as well as graphing. So for instance, with number 6, whether you use math alpha math or you write log of x divided by log of 4 and then plus 3, that's another way you can type that into your calculators so that you can, especially on an older graphing calculator, type that in. So just keep that in mind, that that's why the change of base formula is really handy to you. And knowing these properties can also be pretty handy when it comes to simplifying. Okay, and I'll skip 4, but if we just look at 5 quickly before we end today, if we were to start moving this around so that we have log 2 squared, right? That means that this is like saying log of 25 plus log 4, which that addition would turn into multiplication inside the same log. And we know that log of 100 is just 10. Oh, sorry, not 10, 2. Because log base 10 of 100 is 2. So this mentally allowed us to solve this versus having to type all of this into the calculator. But let's face facts, we're going to probably have our calculator for a lot of these, so it will help us when it comes to solving, and you can always double check in your calculator then. Okay. All right, I know that was a lot of information, but again, if you haven't already done so, I would really take the time to write all of this down, that part that I starred a lot, including your exponential problems as well, because it's not a bad, when it comes to solving, they love exponents on all the standardized tests as well. And then knowing those log properties will help you remember those as well. So I would definitely keep a good track of all of this. All right. Thanks, everyone.